Hi. Um, Today I want to present our work for the ISQED and our work under title Reco Lfsr, which stands for Reconfigurable Low Power Cryptographic Processor based on the Lfsr, which is the linear feedback shift register for trusted IoT platforms. This work it has been done by myself and my students Russell Hu and Kazutomo Yushi from Oregon National Lab, Wenmei Hu from University of Illinois Urbana-Champaign, and Martin Margala from University of Louisiana Lafayette. And I am Mohammed El-Hadedy, the assistant professor at California State University and visiting scientist at University of Illinois and also at University of Louisiana at Lafayette, and a summer faculty fellow at the U.S. Air Force Academy at Colorado Springs. So the motivation, the talk will be distributed as follow. Section will be for the motivation, section for the lightweight crypto and what is lightweight crypto, and also the definitions of what is linear feedback shift register versus non-linear feedback shift registers. And also one of the candidates of the LWC lightweight crypto competitions is Tiny Jumbo, which is based on the non-linear feedback shift register, the architecture in the hardware and how we dealt with this, and the result of the implementation and the conclusion and remarks. So motivation. So of course, security is a very important aspect that it needs to be covered nowadays, especially with the new era of the Internet of Things and IoT. IoT as itself, it's basically you are trying to build the computers and you're trying to build a system that is very capable of doing a lot of processing. It can be sensors, it can be actuators for robotics applications, it can be even cube satellites for security and for army and industrial applications. It can be also small gadgets for the medical devices, and all of these things need security. That's why National Institute of Standard Technology start looking into what will be the best candidate for securing these devices in terms of the crypto and cryptography applications and cryptography algorithms. That's why they launched the lightweight crypto competition. Of course, infinity of application from military, from industrial application, for even hobbyists will benefiting from having this crypto algorithm really quite tiny and cooperative without consuming energy and resources on the chip. Like for instance, industrial walkie-talkie, and actually my research team is working on delivering a crypto processor that will be fitting into small devices as a walkie-talkie and drones and extra and even sensors. What is lightweight crypto? So National Institute of Standard Technology, as a leader of the standardization over all the world and United States, start thinking about that conventional crypto algorithm is not the best for tiny devices. Like for instance, your Fitbit, iWatch, those devices are really hungry for energy, and of course it's consuming too much energy. Some of the companies are doing really great job, like for instance Samsung, Fitbit. They are their battery lasts for like days, while iWatch it has to be charged every night. Of course, security for exchanging the data from this gadget like iWatch or Fitbit or Samsung Galaxy, they will move the data through Bluetooth, and the Bluetooth secured by the AES-128. But AES is a block cipher, and of course, block cipher is really quite great as a concept for security, but it's actually poor of the idea of authentication. That's why authenticated ciphers is very interesting, because you sign the block, every single block you send it from point to point, and of course that will be saving the integrity and identification. That's why National Institute of Standard and Technology put in the consideration the limited devices application, like tiny devices from the power and resources perspective, and launch the LWC, which is the lightweight cryptography competitions. They started with round one, 57 candidates. They submitted most of their applications as authenticated ciphers, and optional, they were submitting hash functions. Then, the NIST downsized this competition into 10 candidates. And those 10 candidates, some of them were actually using the sponge constructions, which have been created by the team who worked with Shasri Kachak. And they produce ASCON. And by the way, this is one of the examples of those 10 candidates who work with sponge constructions. And actually, luckily, the sponge won the competitions as a ASCON, and that was officially released in the February 7, 2023. While some of them were actually using nonlinear feedback shift registers, and it's actually Tiny Jumbo. And even though that it's not meant to, it didn't make it to be the new standard, but it's still applicable and feasible to be used for a wide range of the tiny devices. Okay, so we need to know the story of the Lfsr. So Lfsr stands for the linear feedback shift registers. And by the way, linear feedback shift register is really quite interesting for a wide range of applications, like stream ciphers using linear feedback shift register, smart cards, RFID. They are really quite smart and they're really quite good because they are lightweight. But there is a problem with Lfsr. Lfsr, it's actually can have a security breach. That's why if you look into most of the famous Lfsr like Galileus and Fibonacci and Lfsrs, they are really good for some applications, but they're not really good for crypto. That's why they made the non-linear feedback shift registers, which is really quite famous for the crypto applications. And of course, if you look into the NLFSRs, you will find out the Grain, Tiny Jumbo, Astra Branch, and Kellogg. Those are the most famous algorithms are based on the NLFSRs. Okay, let's look into Tiny Jumbo. We said Tiny Jumbo is one of the authenticated cipher. That means every single block, the data will be broken into blocks, and every single block will be by itself signed and sent to the receiver. Then the receiver will be verifying whether that the sender is the one that authenticated or not, and based on that, it will be decrypting the data. Tiny Jumbo came as a package, which is multiple variants designated for multiple applications. So there is 128-bit key, 192-bit key, and 256-bit key. And of course, every single version has its own security margin. The highest in the security margin is the 256. The lowest is the 128-bit. Of course, all of them, the backbone of the computation is the NLFSR, which is 128-bit wide state registers. And as you can see on the slide, the example of the 128-bit in front of you is actually meant for the 128-bit version key. Of course, if you look into it carefully, you are actually using XORing process for a certain location on the registers and feeding back as a shift register with looping into the state registers. And you do this multiple round, iteration-wise, and that will be strengthening the security margin. Looking into the stages-wise of the Tiny Jumbo, you will find out that, it's between initialization, associated data, and encryption and finalization. So think about it like this. Authenticated cipher, what is the best candidate for it? The network packets. So in the network packets, you have a header and you have the data itself in the packets. So of course, the header is the associated data. So you initialize, you bring the nonce, which is very well known in the blockchain, combined with the key, and you process this to bring the initial state that will be taken by the associated data. And the associated data will be truncating the data, which is associated like a header coming from the Ethernet data-wise, and you will start feeding it piece by XORing that piece into portion of the state. And of course, that will be running rounding of the NLFSR that we mentioned in the previous slide. Once you are done with all the associated data you already have on mind, you will move into the blocks of the data, and you will start feeding block after block until you finish the whole entire message. Then you process the tag, which is a finalization, and this tag will be sent as a proof that you are the owner of this set of the encrypted data. You will send it to the receiver. The receiver will do also initialization, also associated data coming with the data, and then he will feeding the encrypted data as a message, and the data outcoming of this, it will be the decrypted data, and you will look into the tag to verify whether that that have been sent, for instance, by myself as a Muhammad, or somebody manipulated the data, and then you can figure out what's the problem, and you stop the communication channel. Now, architecture-wise, if you look carefully in what we already have done, we built multiple iteration of the 1-bit NLFSR, as you can see on the left side of the slide, and we cascaded in a way that we can get into the 128 NLFSR. And if you look carefully how we did that, we built a kind of edge detectors that will pass into the registers and figure out, based on a counter, which stage out of 128 of those will be in, and from there you can get the state out, which is basically the output of an LFSR. Then we start thinking, what will be the best scenario for this? Is to build a custom hardware, or to use actually software hardware partitioning. And we came into embedded system will actually benefit from having software hardware. And of course, FPGA is the best candidate for that. That's why we use microblades as a soft core processors to do all of the initialization, associated data, and also the message embedding for encryption, decryption, and finalization for providing the tagging, while the NLFSR itself will be migrated in the reconfigurable part of the FPGA and passing the stream of data through Axibus to the main microblades and passing this back and forth. And of course, microblades doesn't have operating system. That's why we embedded the Axi timers and a UART to push the data through the computer. So the Axi timer will allow us to calculate the execution time of this whole entire process. The board that we used for collecting the data, it was the RTX 700T version, which is an Nexus A7, which is dedicated for the student's application, and of course is a good candidate for the low power application and the tiny devices. Collecting the data by running Vivado, we find out that we consumed around 610 lookup table and 505 flip-flops, enough for the NFSR, while the system using the microblades was actually taking 3040 lookup table and 2443 flip-flop and around 32 BRAMs and 5 DSP for doing the process of the microblades. The whole entire system was running in 100 megahertz, and actually we built our NFSR to be above even 400 megahertz, but we ran 100 megahertz because microblades running in 100 megahertz. But this design can be actually modified to work in a multi-clock domain by having a kind of FIFO in the middle with double buffer, which is allowing for the system to be speeded up really significantly. Looking into the execution time, by implementing the whole entire NLFSR in a software and without NLFSR on Axi, you will find the one with Axi doing a great job by running 1,000 encrypting, decrypting multiple times, 1,000 times. You will find that with the proposed NFSR as a reconfigurable part connected to the Axibus, we get actually 2.17 time improvement execution time reduction than the purely implementation of the NLFS Tiny Jumbo on the software side of the microblades. Also, in the time scaling, you can look into the graph and you will find out that the optimized implementation of NLFSR did a great job compared to the NLFSR software and proposed hardware, and of course comparing onto the optimization and the software, as you can see on the slides here. So the software optimized NFSR was actually the lowest at the time compared to the rest of the implementation. Also, we thought about the power by calculating the power management using a practical way, because Vivado will never give a power estimations as a practical. That's why we connected the USB into the to the board, and we look into the power, and we calculated the power consumption from the software as a purely NFSR with tiny jumbo, and proposed NFSR Lfsr reconfigurable onto the fabric of the FPGA, passing the data through the Axibus. Conclusion: the proposed NFSR we already have demonstrated 2.17 time improvement. We minimum actually 6 milliwatt per hour increase in the power consumptions, while performing really quite faster. Additional steps show better scaling with the time compared to the software, and we actually didn't use that much for implementing the NFSR, which is 610 lookup table, 505 flip-flop, which is almost 0.5% of the resources on the chip, while the microBlaze took the whole entire system by 3,040 lookup tables, and that's 2,543 flip-flop, 72 BRAMs, and 5 DSP for the whole system. Future work investigating the reconfigurable and dynamic reconfiguration by actually dedicated part on the FPGA that will be flipping pre-calculated NLFSR that increased or decreased the size of it based on the need of the whole entire things, while the static part, it will be the microBlaze as a watchdog looking into the whole entire system. And on top of that, building one tiny jumbo that will be running all the variants of the tiny jumbo with different NLFSR. We want to thank all the sponsors: UIUC, Lafayette, Reco IoT was the company that actually I built as a CEO, Reconfigurable Internet of Things, US Air Force Academy, and Cal Poly Pomona, and my lab, Reconfigurable Space Computing at Cal Poly Pomona. Thanks a lot for your time, and feel free if you have any questions. I'm here to answer, and have a wonderful, great day. Thank you. Bye.